Welcome back to part 2 of our lesson on roof-mounted system considerations. In this section, we are going to talk about loading. So let's get right to it. When we are talking about roof loading, there are two things that we need to consider. The first is the static or the dead load, and this is really the weight of all the stuff on the structure that is steady and stays in place for the life of the structure. When we're talking about our PV system, this is going to be your modules, your racking, any ballast if it's a ballast mount system, any balance of systems equipment, the inverter if the inverter is on the roof, microinverters, DC to DC converters, anything that is part of the structure or things that are on top of the roof. Could also include things like HVAC units. We see in the bottom right hand photo here there's some type of air handling unit here. That would be a static or a dead load. Again, these are all things that go on the roof and stay on the roof. The other roof load we need to consider is the dynamic or live loads. These are things that change. Things like environmental conditions, wind, water, any kind of snow or ice, seismic forces from things like earthquakes, construction crews coming and going, the tools that they're using, the pallets of modules that they're going to be putting on the roof temporarily. The different parts of the roof are going to have different dynamic or live loads, and we're going to talk about this a little later on in this section. Specifically, we're going to be talking about wind and how that impacts the dynamic load in different areas of the building. Now, our arrays need to stay on the roof. That's a pretty obvious statement. We don't want to put something up on the roof that's going to come off the roof. So there's a couple of different ways that we can keep our array attached to the building. One of the most common ones, especially with structures that have wood construction, are lag bolts. We're going to talk about how to calculate the uplift force on a lag bolt in a little later section of this presentation. We need to ensure that those lag bolts are properly sized for the site and for the load that's going to be on them. Now we can see in the picture on the right here that this lag bolt was not installed properly. The lag bolt needs to be installed in the center of the rafter. This one obviously is blowing out the side of the rafter. That's not going to have the calculated withdrawal force on it, so that needs to be taken out and repaired. Another way we can keep our array in place is by using ballast. So this is typically on a low sloped roof. We use racking systems that are designed for this specific application, where we put additional weight on the racking to keep that racking fixed in place. It's really important that that system is engineered for the specific location, the specific racking, the specific module type. I have seen systems, ballasted systems, where there was a wind event and it rolled the racking up like a Tootsie Roll. Just took the leading edge of that rack and rolled the entire array up into a little round ball, basically. So obviously that system was not engineered properly for that location. We may need to attach the ballast mounted systems in some places, especially places that have earthquakes. We want to make sure that if there's an earthquake that system doesn't shift on the roof. So we may need some attachments of that ballasted system. There are also many other types of attached systems. We have a lot of different attachments for metal roofs. Some standing seam metal roofs have clamps that attach directly to the seam. That's a really great option for a standing seam metal roof. We can also through bolt instead of lag bolting. So we would have a bolt that goes through and maybe wraps around the rafter to keep that rack in place. And we also have different types of anchor bolts, say for concrete roof construction, which we commonly see in Latin America, where we would drill into the concrete and install some type of expansion bolt that anchors the system onto that concrete roof. Many different ways to attach systems to roofs. They're going to vary depending on the roofing type, depending on the structure that we're attaching to, and the racking that we're using. So make sure that you investigate the proper racking and proper attachment for the situation that you are going to be installing the PV system in. Let's talk a minute about rail-based mounting systems. These are systems that are typically flush mounted to a residential roof. That's their most common application. We see a nice little diagram here. We have the rails running horizontally across the roof. In this application, we have 2 rails that go across each row of modules. The module sits across the 2 rails. We have the rafters running perpendicular to the rails. Each one of these little black dots is an attachment point where the rail attaches to the rafter. In most cases, we are not going to attach the mounting foot into the sheathing. There are some applications where we can do that, but we much prefer to attach directly to the rafter. This racking system has what's called a top-down clamping system. There's an end clamp at the end of each rail that attaches the module to the rail, and then between each module there's a mid clamp that attaches the 2 modules to the rail, and we have one of those. Each place there is a gap between 2 modules. So this is a very standard layout for a flush mounted pitched roof racking. Now, how the span and cantilever is calculated is going to be different depending on the racking design, the racking manufacturer, the specific rail profile. Some manufacturers offer a light, medium, and heavy duty rail, and span and cantilever are going to vary based on those different parameters of that racking system. So what is span and cantilever? Let's talk about that. Cantilever is the measurement from the last mounting foot in the rail to the very end of the rail. So it's that overhang from the last mounting foot to where the rail ends. Calculating that cantilever is going to be different based on the manufacturer of the rail profile, and the loads of that specific location. The span is simply the distance of rail between 2 mounting feet. So here we can see we basically have a little more than 2 modules worth of span between these mounting feet. The span's going to vary based on a lot of different factors that we've already talked about. The manufacturer of the rail profile, the wind and snow and seismic loading for the location. It could be affected by the distance between the rafters. Maybe the rafters are every 24 inches, so we only have denominations of 2-foot increments. So maybe we could go 36-inch span, but we only have a 24-inch distance, so we have to do every 24 inches. It's really going to depend on that location. Another thing to know is that we can order rails in many different lengths. So the rail itself can actually span many different mounting feet. So that rail may go across different mounting feet spans. That's perfectly okay. We do need to consider expansion and contraction, and we would need to read the manufacturer's instructions to see how long can we run those rails before we need a gap for expansion and contraction. We say this over and over again at SEI. You need to RTFM, read the free manual. It's very important to look at the instructions for the specific system that you're working with to know what its limitations are, especially in certain situations, certain wind loading environments, snow loading environments, and with certain modules. Modules will have different requirements as well. So what data do we need in order to calculate our spans and our cantilevers? We will need to look at the codes in our specific jurisdiction. Our authority having jurisdiction will have specific requirements. There may be rules that say you can only have a span that's a certain distance. That does happen in certain jurisdictions. We need to look at the building characteristics, specifically what is the occupancy of the building? Is it a residential? Is it a commercial building? Is it a school or a hospital? They have different risk categories depending on the type of the building. We need to look at the actual characteristics of the building. What is the roof height? What's the pitch of the roof, the slope of the roof? What is the loading zone, which we're going to talk a little bit more in another minute here? What's the building type? What's the construction of the building? Is it a wood frame building? Is it a metal frame building? What is the actual roofing material? That will have an impact on our calculations as well. Then we need to look at the things like the dynamic loading, especially things like wind speed, wind exposure. What's the snow load is really important in certain locations, specifically the Northeast and the Mountain West in the United States. Seismic considerations, we deal with that a lot in the western part of the United States. And again, what type of module are we working with? How many modules there are? What's the weight of the system? The dimensions of the modules? How long can we span between mounting points? These are all things that we need to consider when we are designing our system. Now this photo here is a really good example of cantilever. We can see the mounting foot on the left-hand arrow there and that rail that extends out beyond that mounting foot. That's the cantilever. Now if that module is typically 35 or so inches wide, it looks like that cantilever is pushing about 2 feet or so, 24 inches. Is that acceptable to the manufacturer? It may or may not be, depending on the wind or snow loading of this specific location. These are all things that we need to know, and we need to make sure that we're not exceeding that maximum cantilever that the manufacturer has specified. Different sections of the roof will have different wind zones. There are 3 different zones. The first is zone 1. This is the field. That is usually the center of the roof. That's the green section in these diagrams. This is going to be where we are able to see the maximum span between attachment points because the wind loading is at its least. The second zone is called the perimeter. These are the edges of the roof that does not include the corners. That's the orange zone in these diagrams. The wind loading in the perimeter is higher than the wind loading in the field zone, so we need to take that into consideration when we are designing our system. We may need additional attachments in that zone. Zone 3 is the corners, and that is where we see the highest wind loading. In the corner zones, we may see the requirement for additional attachments. We may need an attachment for every rafter in those zones. The wind loading may be so high in the zone 3 corners that we might not be able to put our array in that zone. It all depends on the wind loads for the specific region in which you are installing a system. Now the interesting thing is that the zone 2 perimeter a lot of times also overlaps the setback requirements for the fire code. So in some situations we're not going to be able to install in that space anyway, although the distance of the zone 2 and zone 3 areas will vary depending on the wind loads for your specific site. Now, one thing that we need to consider is the load rating of the module. Modules themselves are designed to withstand a certain amount of pressure from wind loading. We need to look at the module manufacturer's literature and see what that loading is. We may encounter situations where the wind loading is so high at our site that it exceeds the rating of the module. In that case, we would disqualify those modules from being installed in that site, and we'd have to find a module that meets the pressure requirements of that specific site. Now, at the bottom here, we see an excerpt from a module manufacturer's documentation that shows the maximum uplift load in pressure. The unit is a Pascal. we can see that in all of these mounting situations, the uplift load is 2400 Pascal, no matter how we mount that module. Now, the downforce load on those modules changes depending on our racking type. And we can see in the second one over here with the rails mounted to the short side of the module, so the rails are parallel to the long edge of the module there and mounted on the short edge. That increases the span between the mounting points of this module, so the downforce load is lower than if we had the rails running perpendicular to the long edge of the module, attached to the long edge of the module. The span there between the two rails is much smaller, and the downforce is more than double. So we have a 5400 pascals for that mounting situation. That is why we typically run the rails perpendicular to the long edge of the module to reduce that span between the mounting points on the module, make it a more solid installation. Some module manufacturers will not allow you to attach to the short edge of the module with the rails running parallel to the long edge of the module, because the module does not have enough structural integrity to be mounted in that type of situation. So you need to look at your module manufacturer's literature and see what limitations there are for mounting those and what the wind load levels are for those modules in different applications. Now, one thing that we can do is use the module manufacturer's structural analysis design tool. This example here is UBuilder from Unirac. In this case, you go into the tool and you put in the zip code for your site, and it brings up all the data that you need to design the system automatically. It brings up the building code in this jurisdiction, the basic wind speed for that location, the wind exposure, the ground snow load, and the seismic factor. Now, the most important thing here is that you need to verify that this information is accurate. This is a typical garbage in, garbage out situation. So if the parameters that you put into this design tool are incorrect, you're going to get incorrect results out of the design tool. Really important to have enough knowledge to be able to verify that information is accurate. Once you put the information in the tool, it spits out this report and gives you the design span. So in zone 1, which was the field, the green segment of the diagrams we saw earlier, the maximum cantilever is 24 inches, the maximum span is 150 inches, which in my experience, which is in the Northeast United States, that is a huge span. In the Northeast, where we have much higher snow loads when compared to California, the maximum span would be significantly lower. We typically saw spans of about 48 inches, so much less than half the span that you see here. Maybe this is a heavy duty rail, which is why the span is so long. When you get into zone 2, the cantilever stays the same. The maximum span is reduced to 136 inches. And when you get into zone 3, those corner zones with the highest wind load, the cantilever again stays the same, but the maximum span has gone down to 117. Not a huge difference in span. You know, those spans are pretty long, so we might not have to do additional attachment points in zone 3. If we were in a place, say Florida, that had a much higher wind speed, hurricane wind speeds, especially if you're near the coast, these spans will probably be significantly lower. So, something we need to take into consideration, keep in mind, we may find that it is easier to just stick with a standard span that we know works for our region. I know in the East Coast, we typically did a 48-inch span between our mounting points. That worked for every situation that we encountered in our installation. So, your mileage may vary depending on what location you're working in and what module and racking manufacturers you are working with. So again, RTFM, read the free manual and make sure you know the limitations of the equipment that you're working with. That's the end of part 2, loading. In the next part, we are going to talk about how to select lag bolts for mounting into structures with wooden framing. So join me for that part when you're ready. Thank you.